I think we can slowly start today's webinar. Once again, good morning and welcome on our second webinar organized within Support DHC project. My name is Anna Fijas and I'm a project manager in Association of Municipality Polish Network Energy City. I know this is really a wrong name. The short name is SMEG, and we are the partner in Support DHC project. And I'm pleased to be your moderator for today's session. So today we will focus on upgrading the heat, practical strategies for decarbonization existing district heating networks. This webinar is dedicated for public authorities, utilities, and operators in countries where district heating is already well established, but still heavily dependent on fossil fuels. So thank you all for joining today for this session. Before we begin with the presentation, I would like to briefly remind you the content, let's say, of today's event. Like I mentioned, this webinar is organized under the Support DHC project, which aims to accelerate the integration of renewable energy sources and waste heat into existing district heating and cooling networks. So in our project, we are working with operators and local governments to analyze existing systems, identify decarbonization pathways, support investment and transformation plans, and build capacity for integrating renewable energy sources and waste heat. So with this background, our webinars brings together really great experts from different countries who share their knowledge with us today. That's how it looks our agenda for today's webinar. We have 4 presentations and 4 great experts. We will start with the introduction to the Energy Pro Excel tool. Then we will hear more about practical approach and lesson learned from Lithuania and Austria. And we will finish with the role of thermal energy storage in decarbonization of district heating and cooling system. So as you can see, today webinar will be very practical and for sure very useful for all of us. And at the end of our event, of course, will be a time for a question for our speakers. Like I mentioned, we have 4 speakers. I'm very glad to welcome here today. Our speakers, we have Niels Beck Larsen from Plan Energy, Vytautas Džiuva from LSTE from Lithuania, Stefan Redschizeger from Intec, and Abdul Rahman Dasha from Austrian Institute of Technology. So many thanks for joining us today. And before we start with the presentation, I would like to mention some technical issue. Our webinar is being recorded and will be available on Euroheat and Power YouTube channel and on Support DHC Replication Hub. This is a place where you will find many interesting materials, including tools, guidelines, of course, webinar recording, presentations, and many more documents which will be developed during the implementation of Support DHC project. And you can find it on www.replicationhub.supportdhc.eu. And one more information for our participants. If you have any question, please use this Q&A box of the bottom of Zoom. And like I mentioned at the end of the whole presentation, our speakers try to answer for your question. Yeah, so for the first speakers, I would like to invite Niels Beck Larsen. He has more than 40 years of experience in the field of energy technology. Niels has led and contributed to the pioneering work across Denmark's public and private energy sectors. Today Niels will present the Energy Pro tool, which supports operators in analyzing and optimizing district heating system. Yeah, so that's all from my side as an introduction. And yeah, Niels, the floor is yours.
Thanks, Anna, for the introduction. And as you said, I will then present the Energy Pro Excel tool that has been developed in support DHC. The agenda for the presentation is on the left side, the Excel elements in the tool, and on the right side, you can recognize perhaps some figures from Energy Pro or screenshots from Energy Pro. And the basic in the tool is that you actually print the report and copy them to clipboard and integrate them in the Excel files. For the tools, I have been prepared a guide. Won't go any detail with that, but as you can see, there are 13 different plant types that are integrated in a tool and always be integrated. And with the tool, you can make feasibility calculations of all kinds of renewable energy and compare it to different other decarbonization technologies. And also part of the tool is actually how to meet the threshold or the criteria and energy efficiency directive. That's an integrated part of the tool. So you have some figures on that. As I said, the main thing that the 5 standard reports from Energy Pro: cash flow annual, energy conservation annual, on the catalog of economic assumptions, and similar for technical assumptions, and then the annual environmental reports. They are the link between Energy Pro files and the Excel tools where you can later present the results. So for all the technologies, you can have the total and specific cost for the different technologies, and the costs are divided in operation and maintenance, capital costs, fuel, etc., as a normal practice in feasibility studies. And of course, there are some basic fuel costs. And one of the main things in the tool that you can actually have a figure where you can compare the production cost for the different technologies. And you can see here on the bottom right, then a heat pump based on ammonia will have the lowest production cost in this mix. How to tailor-make the tools to the local condition. Of course, you need to adjust the energy prices to the country and location. You need to have some kind of temperature details of the location, so you can actually find out how your heat demand varies during the year. You should define non-availability periods, that's an Energy Pro word, for the plants that you don't have and are excluded in the calculation. And all the plants should, of course, be resized to the heat demand that you have on your location. And you shouldn't, to what I have done here in the presentation, you shouldn't make it with a number of small plants, but you should, of course, have some other kind of tools to make a calculation of how high a percentage of the heat pump should cover, and the other technologies and peak and reserve loads, of course, should also be able to fulfill the full heat demand. So these are the Excel files that are included, and scenario 1 is with fused plants, where scenario 4 have all the 13 plants active in the scenario. And in scenario 1, the heat pump is basically the base load of the calculations. You can download, I think Laura just managed to put the files on the replication hub, but here's a link to where you can find them in the support DHC, but later there will be a link to the replication hub where you can find the files. What have been used besides the Energy Pro? We have also taken the figures from the Danish technology catalog, where you have operating and maintenance cost, investment cost for the different technologies, and that are included together with the figures from Energy Pro and are the basis for the calculations. And as I said, here in the bottom, you see the different reports in the Energy Pro 5, where you can actually integrate that in the Excel files for the calculations. And for instance, here, if you have the cost, then you can find here on the top, you can find a copy to clipboard, and then you can actually copy all the data into the Excel files. And if you see here, it's a total cost for this scenario, and there's a number of links to the report or the cash flow report that you have here to the left. And of course, you have to paste the data into cell A1. All the costs that are included in the model can be used or not used in how to calculate the strategy, because Energy Pro calculates the cheapest technology for an hour, and you can tick or untick whether the different payments should be included in this calculation. And it's a little different in Energy Pro and for 5.0 and Energy Pro 4.9, but basically it's the same, where you tick or untick the different kind of costs. A new feature in 5.0 is that you can actually have an overview of what kind of costs that are included in the calculations, and thereby have dependencies on production costs. Scenario 1 was the scenario with a heat pump as base load. As you can see, when you have low temperature outside, the capacity of air water heat pumps are lower compared to when you have a high temperature and a low heat demand. And that's of course different in the different scenario, and you have surplus heat and waste to energy plants in the bottom that gives a very cheap production cost. Then of course the heat pump are moved further up in the priority in the calculations. And of course, if you have a reference based on natural gas, then it's basically natural gas all year round. You can have the heat duration curve, or you can make the annual curve from Energy Pro, and someone prefers the duration curve, and I believe some of you prefers this kind of curve. And to summarize all the scenarios that you have calculated, you have all the data or results are integrated in the compare tool in Excel, where you can compare the results of the different technologies. And since we are short of time now, I think I will stop here. Or what do you say, Anna? But
if you want, you have 2 minutes to summarize.
to summarize.
Maybe 3.
Then I could also make the presentation for the heat calculations in the different scenario, and of course the total heat production will be the same in different scenarios, but the variation with the different technologies are different. And as I said, in scenario 1, then the heat pump, ammonia heat pump, will be the base load, and the CO2 heat pump will be the second in priority. And there's a number of different ways to present the results. In this one I haven't seen used before, the donut presentation, but I think it gives actually some of the same result as the circles, but you can actually include a number of different things in this kind of presentation, where you can see this big share here for heat production for the waste to energy plant, where the cost of that heat production is very small in total cost in euro. And you can have this kind of overview for the different scenarios, where you can have the total cost and the specific cost for the cost element, operation and maintenance, fuel, tax, environmental, electricity sale, and capital costs. Yeah, I think I'll stop here then.
Thank you, Niels, for your presentations. And I'm sorry we need to stop here, but yeah, we have only 1 hour for all of the presentation. And yeah, thank you for introduction to the tool and information for our participants. All of this presentation and all of the Excel file from this Energy Pro tool will be available and are available on Support DHC Replication Hub, as I mentioned. So after the webinar, you can also familiarize yourself with this tool. So thank you very much once again, Niels. And yeah, now we will move on our next speaker, and yeah, go to practice also. Vytautas will share practical experience from Lithuanian district heating networks. He has almost 10 years of experience in energy sector with strong competences in energy planning, advanced energy system modeling, development of a sustainable energy solution, and representing DHC sector in future perspective. And he's involved in our project as energy and economy experts, let's say. Yeah, so Vytautas, now it's your turn to present.
Thank you, Anna. Hello, everyone. It is a pleasure to be here and present the lessons learned from Lithuania. And I'd like to introduce everyone. 1 second. It does not working somehow. Can you, I don't know, I cannot turn another slide. Anna, yes? Oh. 1 second. Maybe it's some kind of like, yes, here. Can everyone see my slides? Yes? Okay. First of all, I would like to introduce everyone with Kaunas district heating system. And shortly, I would like to introduce about Neveronis, which has actually main 3 natural gas boilers, which covers annually the heat demand. And the modeling purpose was to establish an optimal heat production plan, ensuring that this district heating system would meet the criteria of efficient district heating system and reaching 90% of renewables and existing district boiler house by developing feasible and economically viable scenarios for the replacement of natural gas. And these recommendations should be used for future 10 years investment plan for Kaunas district heating company. Yes. What was done and what kind of modeling approach and strategy was applied? So first of all, was implemented overview and characterization of waste heat potential of this Neveronis area by identifying wastewater treatment plant potential capacities, industrial enterprises with waste heat potential, also investigated existing Kruna River near Kaunas Lagoon, waste heat potential possibilities, also incorporation geothermal heat sources. And after all these assessments, it was decided further develop and accept the most appropriate one air heat source in Neveronis boiler house. It was identified that the most appropriate natural refrigerant would be CO2 that would be used for compression heat pumps. And after this, the procedure was done for scenario analysis and for finding the best configuration and optimal capacity of new heat generation sources. So it was done and developed with the help of Energy Pro software package in order to identify the optimal mix of energy generation sources for natural gas usage reduction. It was organized six potential scenarios by varying the different sizes of CO2 heat pumps from 0.7 to 0.6 megawatts of thermal capacity with the integration of diverse size of short-term storages, also sizing from 500 to 60. And the scenario 5 and 6 is it has it's unique by additional incorporation of electric boiler and biogas usage in the current gas boilers. And here, I don't want to spend a lot of time. A short representation of all key economic assumptions. The most important aspect is related with electricity price that was assumed to be around 70 euro per megawatt hour for 2030 period of time. Natural gas price would be around 45 euro per megawatt hour, and you can see other indicators. Talking about heat pump, assumed it was according to Denmark manufacturer Fenergy CO2 heat pump that is very suitable for high supply water temperatures in the range of 60 to 80 Celsius degrees. Suitable for low air temperature regimes in the difference approximate around from -10 to -20 Celsius degrees. And also you can see all these economic assumptions like investment, fixed operational cost, variable operational cost, startup cost, and so on that was assumed in the Energy Pro model. Thermal energy storage was organized according the temperatures, according to the supply water temperatures. At the top, the bottom part of the storage was assumed according to return network water temperatures. Additionally, incorporated all the heat losses, and it was assumed 95% capacity utilization. And after all this indications and inputs for the model, at the beginning of the scenario analysis was organized the base scenario representing what will be in the future if no potential investments will be done in this potential boiler house. And it was obtained the results that would be high CO2 emissions, lack of flexibility in existing system. It might be very high natural gas price volatility, and many geopolitical issues related with these natural gas sources. But one more thing important, that it might be kind of low heat production cost of only 65 euro per megawatt hour. Uh, Despite this fact, it was implemented comprehensive analysis of a scenario by implementing, as I mentioned before, 6 scenarios by sizing different capacities of heat pumps with different size of uh, short-term storages, and the scenario analysis provided the outcome that the most optimal one might be alternative number 4 by incorporation of heat pump with a size of 0.7 megawatt with 60 cubic meters short-term storage, and allowing to achieve very fast, simple payback time. The better demonstration can be seen in here. This scenario might have the fastest period payback, but despite this fact, all these scenarios demonstrated a bit higher heat production cost comparing the existing situation using just natural gas boilers. But despite this fact, it was many other good benefits. As I mentioned at the beginning of this presentation, this new facilities would provide a lot of renewable energy, more than 90%, allowing to reach high percent of utilization, and providing a lot of operating hours, and providing a combination of this heat pump working with thermal storage. And you can see how this annual heat production would be demonstrated. Only for coldest periods, we can see that natural gas boilers would be used in order to provide the heat demand for peak regimes, peak modes. And it was found that optimal capacity of thermal storage would be around 60 cubic meters with high efficiency of more than 98%, high capacity utilization, and this would provide a lot of benefits. And looking only to the economical results, this would provide for us to have 12 years payback time. But it was very interesting to investigate more, to do some kind of sensitivity analysis for this scenario, and it was obtained the results that electricity market price will have very huge impact for a final heat production costs for this kind of scenario, and this would might be some kind of fluctuations from 69 to 75 euro per megawatt hour. The natural gas price fluctuations might have the less impact on final production cost, but the biggest impact for final results might have the financial support. For instance, if we would have 40% financial support for such compression heat pumps and the integration of the storage, we can obtain really good financial outcomes, and it can be the very similar average heat production cost like existing usage of natural gas boilers, or might be less. It depends from the future electricity and natural gas purchase price, as you can see in the obtained sensitivity analysis outcomes. And here, the final conclusion of this CONUS case can be elaborated that this compression air water CO2 heat pump with a capacity of 0.7 megawatts and integration of 60 cubic meter short-term storage might be feasible and attractive. only if would be obtain the financial subsidy for at least 40%, and it would be possible to remain in line with the current heat production costs. The biggest, of course, effect of this that this green innovation would reduce CO2 emission from 900 tons per year to 90 tons annually, and this would provide huge advantage for future infrastructure. Also, another case is Alytus. It's a much more bigger city.
Sorry, Tautas, for interrupt you. I know you have the second cases, so
yes.
if you could summarize it quite quickly, but for this that would be great.
All right. So very short describing about this concept. It was the integration of short-term storage to the existing infrastructure. And it was done some modelings, also incorporating Energy Pro and partial equilibrium model. And the optimization was done by organizing three kind of scenarios with future forecast assumptions. And the interesting part that was really useful obtained outcome of this comprehensive analysis, that short-term storage might be feasible in the existing biomass CHP. And huge economic effect might be achieved financially if it would be integrated together for a heating season and incorporating independent heat producers for natural gas reduction purposes. And for instance, if we would integrate for non-heating season, this would also be very financially optimal for additional incomes of electricity production, and later on you can also see other results that was achieved. But the most important aspect, maybe practical one, after all these investigations, it was obtained that despite many modelings from 500 to 10,000 cubic meters, the potential integration possibility of short-term storage to the existing biomass CHP, it was observed a situation that it is not possible to achieve 100% renewables despite a very huge existing percentage of renewables, only 3%. Because independent heat producers auction system would not be enough. They would operate at full capacity and would not be enough of heat charging capacity for the tanks. But despite this fact, it was selected 3,000 cubic meters as an optimal one. Many tons for CO2 reduction and other benefits like electricity, additional sales. So good results were achieved, and that's in short term. Thank you.
Thank you very much for this case studies and for giving us a closer insight at the Lithuanian approaching of modernization the HC system. Now we can go to Austria. Stefan is a scientific researcher at INTEC, and his main research areas include urban systems analysis, district heating and cooling system, renewable energy system, and biomass combustions. And now, we heard more about lesson learned from Austria. So Stefan, the floor is yours now.
Thank you, Anna, for the introduction. Welcome to all participants also from my side. For those who don't know INTEC in Austria, we are a research institute in the middle of Austria, close to Graz, mainly dealing with renewable and sustainable energy in different fields, ranging from renovation of buildings, industrial processes to district heating. Me personally, I'm working in a group called Citizen Networks, which mainly deals with everything related to district heating. As Anna introduced, we're the Austrian project partner in Support DHC. We are responsible for the cases in Austria and for our frontrunners in Ukraine. And today I can talk a bit about our Austrian frontrunner, Kapfenberg. Kapfenberg is a small town in the middle of Austria, in a valley leading to Vienna. As you can see in the picture, space is a bit narrow. We don't have a lot of land, but on the pro side, there is a lot of wood available in the area. District heating in Kapfenberg was already erected more than 50 years ago, at that time based on waste heat from a steel manufacturer. But when the network was extended, this was basically done with natural gas. So at the moment, we have roughly 80% natural gas in the energy mix and only 20 or less % of industrial waste heat. That means there is still some work to do in Kapfenberg. We've been working with Kapfenberg for a couple of years now. And within Support DHC, our aim is here to really support them with the planning of this whole transformation process, to integrate the different heat sources that are available. We have already dealt with which heat sources are available in a previous project. And now we're at the stage of really planning the implementation and get everything in line with EU regulation. Our work in Kapfenberg at the moment is almost done. That means we are just finalizing results and then provide some evidence documentation for the project and really bring everything on track to build the new district heating system. A bit of an insight into Kapfenberg itself. You can see in the middle this blue district heating network in the circle. This is the district heating network at the moment. It is, as I said, supplied by gas at 2 locations. And we have 7 more small district heating systems in the outskirts. And the idea here in Kapfenberg is to implement all of them into one greater district heating network. So include all the smaller ones and also do that with a completely renewable energy basis. If we're looking a bit towards these different energy sources, as I said before, we have 2 district heating or 2 gas-fired plants in the center of the city at the moment. They supply the main network. There is one smaller one on the outside. And the idea is that these gas-fired systems shall be really closed. They will be shut off in the future. Then we have one plant, one location from the steel manufacturer, First Alpine, located in the center of Kapfenberg. This one does already supply heat to the network. The idea is really to get more heat from this system. One tricky thing here is that this plant is only operated from Monday to Friday, so we don't have the heat available all day long or all week or all year long. Another waste heat source, which is very attractive, is a paper mill called Norskeskog with a higher capacity, up to 10 megawatt. And this one is operated 24/7. So this will be most likely a good base load for this whole system. And what is also critical is that a new central heating station will be built. It's planned a bit outside where we will have a biomass boiler. We don't know yet how much this biomass boiler should be in operation. It will be owned by the district heating operator. It will be operated on demand. The idea is also to integrate the power to heat system, if possible, and if it makes sense. And of course, there will be a backup system based on gas. And what was already mentioned before, storage is extremely important. And I guess we will hear more in the next presentation from AIT about thermal storages. In the first presentation from Niels, we heard that usually we have constant demand, and then we were looking into different solutions on how to satisfy this demand. But when we are talking about an expansion of a network over a couple of years, and in case of Kapfenberg, this means tripling the network in length. It means more than doubling the energy demand. Then a forecast of the demand is rather tricky. For us, that meant we did look into different scenarios on the demand. This can be the total heat, but also the peak load. And especially when it comes to peak load, it means that either you build larger storages that can cover these peaks, or you would need different energy sources like gas boilers that can cover this peak demand. The idea here in Kapfenberg is to really provide heat without any fossil resources. So the way to go here in this case is definitely to cover everything by storages and with a biomass boiler or the waste heat. As in the other cases, we set up our Energy Pro model, and I would just like to mention two things here. On the one hand, the demand is not constant. We're looking at a certain demand at the moment and an expansion plan. So what we did in our simulations is really to take this real expansion plan, or at least the plan, into account and increase the demand over the years. And the second thing is that we are looking into coupling the heat network with the electricity network. One of the aspects here in Kapfenberg, or one of the to-dos, was to look into the power-to-heat system. And when you are looking into power-to-heat, you don't have constant costs for your energy source. In case of biomass, it's rather easy. In case of gas, it can be rather easy. You have a constant price, constant costs for your heat production. But when you're looking on the electricity market, then the costs are fluctuating, as we all know. So in our case, the question was, which costs do we really use, and when is it profitable? When does it make sense to use this power-to-heat system? And we indicated this here at the bottom a bit with different lines. So our approach was to use the electricity from the grid and from an own PV system, of course, if the price is below a certain level. And that gives us a lot of different variations and data to evaluate later on. Regarding the demand from our profiles, the results were as estimated. Basically, in our calculations, it did show that waste heat, mainly from the large paper mill, from Norskeskog, and also waste heat from the steel manufacturer, will be able to cover most of the heat demand in all scenarios, roughly 99%. The biomass boiler will only be in operation as a peak boiler, and we should not need a gas boiler in our scenarios. But as we all know, plans can change, and we will see where we are in a couple of years in Kapfenberg. The power-to-heat thing was a bit more work to look into. As I said before, we did take a certain price level for the electricity based on the day-ahead market in Austria, and extrapolated that into the future with a certain increase in price, and then looked into different capacities of a power-to-heat system to get a first idea what does make sense for such a system. And the important thing here is really to take into account all the costs that are related to this system, be it CapEx, be it OpEx, also funding, as we heard from our Lithuanian colleagues before. In our case, the different calculations and the results showed that a capacity of roughly 2 megawatt would make sense in Kapfenberg, and it would make sense to buy electricity from the grid if the price is below 40 euros per megawatt hour. This would decrease the overall heat production costs. And if we're looking at these heat production costs a bit more in detail, we did just a rough comparison here. On the left side, the basic scenario where no power-to-heat system is included, then a small power-to-heat system that can be based on the own PV system without an expansion. This will not do a lot. And if we really build a 2 megawatt power-to-heat system, then we see that the levelized costs of heat, our heat production costs, will decrease further. And this would be our optimum case in this scenario. If you look a bit at the numbers, this levelized costs of heat, we're talking about really small changes. So we looked a bit into this total amount of money that accumulates over a couple of years. In our case, if we look at the time span of 20 years, we would need to invest roughly 300,000 to 180,000 euros, but we would get savings of roughly 600,000. So over 20 years, we would save 300,000 euros. And this is kind of a good basis for a decision. since we are talking about a larger district heating system, 300,000 euros over 20 years is not a lot of money. And the important thing here is that this is a methodology that allows the operator now to have a good basis, a solid basis for a decision, if it even makes sense to look into this power to heat system, or if they should address their focus to something else. We haven't come to a conclusion for Kapfenberg yet, but we're going towards the end with our simulations, with our scenarios, and with the discussions. Based on what we did so far here is, I think the important thing is to really look at costs over this whole lifetime, or at least this long time span. When you invest something, you need to look at 20 years, 30 years. Demand coverage is, of course, the most important issue. Customer of a district heating system needs to be satisfied. And we did reach a rather, I would say, a result that makes sense in our case. We will see if this will be being built in reality. We'll see that in the next couple of months, years. Regarding the Energy Pro application, I think it's important that the demand development is really estimated as good as possible, including variations, because we don't know who will really connect to our district heating system. So this needs to be taken into account. And also these operational constraints are something that are, I would say, very important to be considered. If a waste heat source is available 24/7, if it has limitations, if there are some shutdown periods, then the heat needs to be provided by some backup system. And also the price developments. As I said before, biomass is rather easy, gas is rather easy, but if it comes to fluctuating heat sources like electricity, then it gets more interesting. And this is where such an Energy Pro application really has its strength and can give you some certain and well-based answers. And with that, I'm already at the end of my insight into Kapfenberg. Thanks, and back to you, Anna.
Thank you very much, Stefan, for this case study from Kapfenberg. It's time for our last presentation. It came from Abdul Rahman. He's a scientist at Austrian Institute of Technology, and he's involved in several national and international research projects in large energy supply infrastructure, with research interest in large-scale seasonal thermal energy storage, heat pumps, district heating and cooling, and heat transfer in installation materials. And Abdul will present us the role of thermal energy storage in the decarbonization of the HC system. Please, Abdul, the floor is yours now.
Yeah, thank you, Anna. Thank you for the introduction, and welcome to everyone. So as announced, I'm going to talk about the role of thermal energy storage in decarbonization of district heating and cooling systems. But more precisely, I'm going to focus more towards seasonal, large-scale, and underground thermal energy storage in district heating systems. And also next to that one, I'm going to highlight the role of another crucial component when it is coupled to district heating, how much decarbonization you can achieve. But before we start, I would like to ask the control whether they can give me also laser points so that I can start. That would be great. Meanwhile, a good start would be always to ask why we would need a seasonal and large-scale thermal energy storage in district heating systems. So the motivation behind this technology is that if you consider the following figure, you might see on the left-hand side of this figure that we have a graph that shows to you the dashed line representing the space heating demand and also the continuous line representing the solar heat availability during summer. So basically during summer you have surplus heat that you would like to capture via a number of solar thermal collectors, then you inject it into a large-scale thermal energy storage via charging, and then later during winter, when the dashed line, the space heating demand is at highest and the solar heat availability or the renewables heat might be at lowest, you start discharging. And by that, you complete one cycle on annual basis. This complete cycle, we call it a seasonal cycle, and that's why we have a seasonal thermal energy storage. Worldwide, we have currently many successful examples about seasonal or large-scale thermal energy storage. Most of them are located in Denmark in the form of pit thermal energy storage, as you see with Marstal, Droninglund, Gram, and Voyens. All of these are coupled with another magic technology, I would call it, that is called heat pump. We will see later also the role of the heat pump. So talking about seasonal thermal energy storage or large thermal energy storage brings me to introduce to you one of the Horizon Europe running projects that's called Interstores. Interstores is started by the year 2024 and is planned to last until the end of 2027. We have a budget that is slightly over 11 million to bring 14 partners from 9 different countries to collaborate for 2 demo sites. One demo site, you find it in Germany, that is on the left-hand side, that has a total volume of around 18,000 cubic meter for 3 basins, as you see them in here. They form all together pit thermal energy storage that is filled with the gravel to form the so-called water gravel thermal energy storage. On the right-hand side also, we have the second demo site, which is the world's largest seasonal cavern thermal energy storage with a total volume of 1.1 million cubic meter. In both, we have large-scale thermal energy storage and we have heat pumps. So moving to our case study that we are considering, unfortunately, I couldn't reach any disclosing with our operator or the operator of the district heating system that we are considering. So we aren't going to say which city, but it's a real life situation, real life scenario that we have currently here in Austria. So let's call it a representative city that is in Austria with a district heating system. And the city has a population of around 225,000 inhabitants. The annual space heating demand, only space heating demand, in this case, we have 333 gigawatt hours, and the supply temperature during winter goes beyond 80 degrees Celsius. This district heating is mostly fossil-based or fossil fuel-based, so conventional with natural gas, and the goal is to move it or to transfer it into solar-assisted district heating system. So unlike the former presentations, we use in here Daimler, which is a dynamic simulation tool with our components to understand the integration and to improve also the operation over the long run. As you see in here, we have again the boundary conditions from the district heating system. So on the top, on the left-hand side, you see here with the red line, the heat load, focusing only on the space heating load. That's why during summer we have 0, and the load peaks at around 165 megawatt. Also, on the bottom of the left-hand side, you find in here also the supply temperature. During summer, we have a supply temperature that is almost constant at 65 degrees Celsius due to the constraint of Legionella. And then here we have the ambient temperature. So moving to the results, as I said, the goal was to transfer this district heating system from a conventional district heating system into more renewables power district heating system. So the first thing that came to mind, solar assisted district heating system. If we consider this one, after many simulations, we allocated I would say the optimal solar area or aperture area, and that would be around 76,000 square meters with a GHI, global horizontal irradiance, of around 1,200 kilowatt hour square meter per year. We have also on the demand side all the information, and right now the main challenge is to find the type of the seasonal thermal energy storage, whether it is a buried tank thermal energy storage or a buried pit similar to Denmark, and also what is the optimal volume. So as you see here on the left-hand side, on the vertical axis, this one you see the solar fraction, and on the horizontal axis, we vary the volume of the seasonal thermal energy storage, starting from 210,000 up to 360,000 cubic meters for the 2 types, TTES and PTES, the tank thermal energy storage and the pit thermal energy storage. What you see in here is that the pit thermal energy storage, the red line with the I would say with the red marked circles, outperforms the tank thermal energy storage. It has slightly 1 up to 2% more solar fraction, but this is not a real outcome. This is due to the thermal losses that we have. The pit thermal energy storage for the same volume has more lateral area and surface area, and that's why more thermal losses. So it means that we can accommodate more solar thermal to that one. If we want to consider another indicator, that would be the thermal efficiency of the seasonal thermal energy storage. So on the right hand side, you see in here the efficiency of the seasonal thermal energy storage for the two technologies. And what you see in here is that the tank thermal energy storage has a minimum efficiency of around 80% that increases up to 90% for the volumes that we are considering, while for the pit thermal energy storage, the red line in here, it starts slightly below 60% up to 75%, as you see in here. So we could say, you don't see it here, it seems like due to merging problems, but it could be observed that our optimal volume would be the 330,000 cubic meter, as you see in here. The main reason behind that one, if you consider the tank, beyond the 330,000, there is very marginal increase in the solar refraction and also in the efficiency. To confirm that one, we also here consider the avoidable CO2 emissions in the entire system. And in here, compared to our reference case, you see that we could achieve with the 330,000 cubic meters for both technologies, we could achieve up to 16,500 CO2 tons that can be reduced or can be avoided, okay, by replacement of the natural gas. So our optimal volume would be 330,000 cubic meters, and also the optimal type would be a tank thermal energy storage. Then there was another question, what would we do with the backup boiler? How can we reduce its operation and also not only the duration, but also the capacity after that? So we propose also to install a heat pump coupled to the tank thermal energy storage, the seasonal thermal energy storage that we are considering. And here, for example, on the left-hand side, you see on the horizontal axis, we varied the capacity of the heat pump from 2 megawatt up to 12 megawatts. On the vertical axis, we have the annual heat output from each heat pump capacity. And what you see in here, it increases as we increase the heat pump capacity, which is quite logical. On the right-hand side in here, you see also the seasonal coefficient of performance, which is annual averaged, as you see in here, and it decreases as we increase the capacity of the heat pump, which is again quite logical. So it drops from 2.85 down to around 275. Then on this slide on the left-hand side, you see that via the installation of the heat pump, we can increase the solar fraction from the reference case where we have only tank thermal energy storage with the solar thermal collector from 25% up to 28%, so 3% extra, if we install a heat pump with a capacity of around 12 megawatt. What does that mean for the efficiency? That means also a boost in the efficiency of the seasonal thermal energy storage by 3% extra. The main reason behind that one, because a heat pump coupled to the seasonal thermal energy storage would allow the thermal energy storage to be deeply discharged from the set point of around 50 degrees Celsius down to a minimum of 20 degrees Celsius, which means extra capacity, extra storage capacity, and simultaneously that means also lower losses, better efficiency, and more accommodation of solar refraction. Now, if we consider as well the avoidable CO2 emissions or the reduction on annual basis compared to our reference case, we can boost it up to 31% if we install a seasonal thermal energy storage with a heat pump that has a capacity of around 12 megawatt. So the key takeaways that I would like to say is that as we are transitioning our energy systems, it's important to pay kind of consideration and awareness to very important and crucial elements like thermal energy storage with large volumes and couple them to heat pumps. The main reason, they can be very good and game changer as we are transitioning in the energy perspective. Also, what we have seen together is that the integration of the seasonal thermal energy storage together with the heat pumps isn't an easy job. It requires detailed planning. You have seen just a couple of results, but what we have behind those slides is that hours of planning, hours of understanding as well, and there are many other results that brings the economic considerations together with the environmental aspect as well. However, what I would like to say is that heat pump integration always pay off together with the seasonal thermal energy storage, and together with both of them, you can achieve up to 30% decarbonization for the case study that you are considering under the boundary conditions that we presented. So to say, I finished right on time. That was all from my side. Thank you all for listening, and I would be open up for your questions as well. Thank you. So the floor is yours, Anna.
Yeah, thank you very much, Abdul, for your presentation. Yeah, and thank you once again to all of our speakers for the insightful presentation and for sharing with us their experience and knowledge about this topic. I saw that we have some questions. One question was to Vytautas, but I see it's already answered. I see the next question. So if you could stay with us a little longer, so I read also. Thank you for interesting and useful information. With your permission, I have a practical question. What best practices would you recommend for Ukraine in the context of where, specifically for cities near the front line, such as Sami, Konotop? I don't read maybe another name of the Ukrainian cities, but yeah, I think the question is open. So who would like to answer for this?
I can answer, since we've been working with Ukrainian partners for quite some while now. We've been working for a couple of years with Lviv in the very west of Ukraine, but now in another project also with Poltava, which is more in the east, more closer to the front line. One key aspect for them is diversification of heat generation. Basically, going towards more smaller plants to get more redundancy into the system in case any of the larger systems are attacked. And these smaller redundant systems, they often also serve the purpose that they can be based on renewable basis, be it a heat pump, be it a small biomass combustion plant, and not only one huge gas-fired plant.
Okay, thank you very much. And Abdul, you have some comments?
Exactly. Yeah, I have also a follow-up comment on that one. I would agree also with Stefan on that one. And what I would say is that resilience, and resilience. This is the most important aspect that we need to consider in here. And by resilience, I would go more towards like a bit far and say decentralization of the heat and the power. Though I would always advocate the coupling. In this case, I would go for dispatchability between both of them, though I would also increase the role of the CHP. Redundancy would be also a very important aspect that we need to consider. And I would put a strategy more like kind of emergency-oriented district heating supply. That means we should focus on hospitals firstly, then shelters, and then also the water utilities. These are the three important aspects, like critical infrastructure, so to say. And without the need to promote underground thermal energy storage, yeah, we need also underground thermal energy storage in this case to provide the space heating demand if needed, or the heating demand that is needed by the emergency-oriented facilities, again, like shelters, hospitals, and the water utilities.
Yeah, thank you. Thank you for the comment. Okay, I don't see any more questions. Okay, so once again, thank you for your presentation and for your time. Stay with us a little longer and for engagement to these questions. I think we can go to close to our webinars. I hope the information shared today will support your own work in the decarbonization district heating networks. And on behalf of Support DHC project and our organization partners, thank you very much for joining to us today. Yeah, you can see on the screen the QR code to our project website and the replication hub. So you can visit our websites where we add information about our activities, our project events, webinars. We upload a lot of useful materials on the replication hub, and like I was mentioned in the beginning of our webinar, the Energy Pro tool is also available on a replication hub, so you can check it and use it. And I think that's all from my side. Once again, thank you for joining to us for our participants, and thank you for the speakers. Have a great day, and thank you very much. Goodbye.
Thank you.
Thank you as well.
Goodbye.
Have a great afternoon. Bye bye.
Bye bye.
Thank
Bye.
you. Bye.